Welcome back to our course. Now we will have an example of an inclined beam. The beam DB makes an angle theta with the horizontal. Tan theta equals opposite over adjacent, 6 meters for the opposite, and 8 meters for the adjacent. The horizontal projection of CB is this 8 meters, while the vertical projection of CB is this 6 meters. LCB is the actual length of CB, the actual inclined length, while L-CB is the horizontal projection 8 meters. To compute our reactions, we determine them. We have one reaction in the direction of CA, as CA is a link member. We have two reactions at B because it is a hinge, YB and XB. Note that the length of AC doesn't really matter in our problem. The resultant of the distributed load is 2 tons multiplied by the actual length of CB 10 meters, as this is the length on which the load is distributed. Please note that the distributed load 2 tons per meter run is distributed on the length CB equals 10 meters, while the arm of the resultant will be the horizontal projection 8 meters. 8 meters is the length perpendicular to the direction of the distributed load and so the direction of its resultant. The beam has the following reactions computed. Sigma forces in the x directions equals 0 and therefore xb equals 0. We have a moment about B equals 0 and the forces causing those moments are 2 by 10 by the arm perpendicular to it 4 meters, RA multiplied by the arm 8 meters, and 6 tons multiplied by the arm 10 meters, respecting the signs causing the directions. Please note that all vertical forces have horizontal arms. And RA is 17.5 tons. Sigma forces in the y direction. We take the 6 tons, the RA and YB, which gives YB equals 8.5 tons, and we plot it on our diagram. The beam DB is taken here with the applied loads and reactions just to make calculations clearer. We have the 6 tons at D, reaction at C, distributed load 2 by 10 between CB and applied in the middle of CB. We have also the reaction at B 8.5. Each force is analyzed into a red component to draw the normal force and a blue component to draw the shear force. The distributed load is drawn in a dashed line to remember all through the solution that it is distributed and not concentrated. Angle theta is determined for each load. Please recall that if two lines L1 and L2 make an angle theta between them, then the angle between the perpendicular to L1 and the perpendicular to L2 make also an angle theta. So we have DB making an angle theta with the horizontal. The perpendicular to DB and the perpendicular to the horizontal, which is the vertical, also make an angle theta between them. So we have this angle theta for each load. Of course, the angle theta can be determined in various other methods. However, I believe this is the easiest and the fastest. From trigonometry, the component adjacent to theta, which is the blue component in our case here, has the cosine. So we have a blue component 6 cosine theta and a red component 6 sine theta. Similarly, we can compute the other components for each force. These are the values of the forces computed. Now we are ready to plot the straining actions. Normal force diagram. Note that all values will be plotted perpendicular to this center line. Normal force diagram is plotted by the red forces. The red forces are in the direction of the center line. Note that there is a concentration of normal at C, 10.5 tons, and therefore the diagram has a normal force for C left and another one for C right. Also note that the 12 tons distributed load is the difference in normal between C and B, and therefore we expect the diagram to be inclined in this part. Starting from D, it is clear that 3.6 tons is a compression force and therefore will be plotted below the center line. From D to C left, we have no variation in normal, and the plot goes parallel to the center line. At C, we encounter a concentrated 10.5 tons in an opposite direction, and therefore will be added to the previously computed normal to get NC right. And we plot it on our diagram. Between C right and B, we go for the inclined part by the 12 tons. Note that this minus sign is because the 12 tons are in the same direction of 3.6 tons. And our plot closes by the component of the reaction 5.1 tons at B. Shear force diagram. We plot all blue forces perpendicular to the center line, and again we know that there is a concentration of shear at C, 14 tons, and we expect shear C left different from shear C right with a difference of this 14 tons. Also, the 16 tons component of distributed force makes us expect an inclined diagram in the part CB. Starting from D, our left hand side has a 4.8 tons shear heading downwards, and therefore this is the negative shear and will be plotted below the center line. From D to C left, we have no variation in shear, and therefore the diagram goes parallel to the center line until we encounter 14 tons positive and will be added to the last computed value of shear, which makes QC right equals 9.2 tons, and we plot it on our diagram. Subtracting the 16 tons because it is heading downwards, we have our inclined part until we reach QB. The diagram closes by the virtue of the component of the reaction 6.8 tons. Bending moment diagram. We compute one moment at C, here, and plot it perpendicular to the center line, as all other diagrams were plotted perpendicular to the center line. So we have MC computed from the left part equals 6 by the arm perpendicular to it 2 meters, making 12 meter tons with a tail of the force heading upwards. Here we are. We join the computed value here to the nearest left moment value, D, and the nearest right moment value at B. Bending moment for the distributed load between C and B is a second order, and therefore we have the parabola WL(L)/8. WL is the resultant of the distributed load, 2 by 10. L' is the projection of CB perpendicular to the load, and therefore we have our drop 2 multiplied by 10 multiplied by 8 over the constant 8 equals 20 meter tons, and we plot it on our diagram. This concludes with our example on inclined beams.